Yo, good morning, It's the Wednesday before Thanksgiving. The perfect day to solve another Leetcode problem. Okay, so problem 2369. Relax. Check if there is a valid partition for the array. You are given a zero-indexed array, integer array, nums. You have to partition the array into one or more continuous subarrays. Okay. We call a partition of the array valid if each of the obtained subarrays satisfies one of the following conditions. So if the subarray consists of exactly two equal elements, okay, so 2, 2, for example, is a subarray that satisfies one of the conditions. The subarray consists of exactly 3 elements that are equal, so 4, 4, 4, or the subarray consists of exactly 3 consecutive elements. That is, the difference between adjacent elements is 1. For example, 3, 4, 5 is good, but the subarray 1, 3, 5 is not. Return true if the array has at least one valid partition. Otherwise, return false. Okay, so the nums array is a valid partition array because you can split it into 4, 4, and then 4, 5, 6, right? So just to kind of write it down to make this a little bit clearer. If you have this example where nums equals 4, 4, 4, 5, 6, right? You could split it into a partition of 4, 4, which meets the first condition, right? Because it's 2 equal elements. And then partition of 4, 5, 6, which meets the third condition. Okay, so I think a pretty natural solution for this problem is dynamic programming just by looking at it. Because, you know, if you have any such set of elements, right, like I'm just writing these letters out to specify that I don't know what these variables are, right? If for any node or any vertice, right? For any element, right? This is a solution if either the first condition is true. So if the first condition, if it's a solution up to this point, right? This point E, if what? If this is true, meaning D equals E, right? If D equals E, then there has to be a solution up to this point. I guess another way I can write it, if that doesn't make sense, is let's write these as nodes in a vertice. So let's look at the example problem. 4, 4, 4, 5, and 6. So I guess the idea is, in order for this whole thing to be a solution, that means that there needs to be a solution up to this point in the array, right? So let's think of it like that. So there has to be a solution using 4, 5, 6, right? Because every single node has to be a part of some partition, right? So that means that 6 has to be a part of some partition. So in order for 6 to be a part of some partition, one of the 3 conditions has to be true for this node 6, right? Either 5 and 6 are together and they meet condition 1, which means that whatever happens before needs to also be a part of some valid partition, right, for this system here. So that's condition 1, right? Condition 1 would mean that 5 and 6 are together. It's not true, right? But there's 2 equal. And then the previous system has something true. Or it could be that the partition including 5 and 6 includes 4. And the previous system comes before that. Right? And this could be condition 2 or 3. Meaning, like, if you have a system of edges, a system of values in your array, in order for something to be a solution, you check if that's a valid partition and if everything that came before it is also a valid partition, right? So in order for any partition to be valid, everything that comes before it also has to break into a valid partition, right? So I guess the observation is, in order for one partition to be valid, every partition that comes before it has to also be valid. Okay, meaning if you had a system where it was like a bunch of nodes and then you saw 2, 2 and a bunch of nodes. Well, you know that 2, 2 meets this condition here, right? 2, 2 meets condition 1 because they're both equal. So you could be like, okay, 2, 2 is a valid partition. But the only way 2, 2 will work in the grand scheme of all the valid partitions is if what comes before it, right? If this system can be partitioned up to this point here, right? And then when you look at subsequent elements, right, these will only be valid partitions if everything's a partition up to here. So every time you find a partition, you can check if the element that comes right before the split that you're turning into that partition is also a valid partition, right? Because if you have a system like this and you determine that up to this point, right? Like maybe you determine that up to this point, for example, on the flip side of the coin, if you determine that up to this point, it's a valid partition, and then you ask, okay, well, this is also a valid partition, but it may not be the case that this is a valid partition, the whole thing, including the last X. So you won't be able to partition the system. But if you found that up to and including every X is a valid partition, so when you add 2, 2 and you ask if the previous element's a valid partition, it returns true. Okay. So in order for something to be a valid partition up to a point, so a valid partition up to a point P means that either, so a point P meaning an index, so let's call it an index. So this will be our reoccurrence relationship. So V to an index, so if it's valid, means that V at IDX minus 2 up until IDX, I guess. Sorry. So this would say if this was 2, so this would be condition 3. Or let's make it a little bit clearer. So it's a valid partition up to an index if what? Well, the first condition, right? So if the value at the index before equals the value, talk about nums here. Sorry, guys, I'm pretty tired, so I'm making a lot of stupid mistakes here. If the nums at the previous index equals the nums at the current index, that's condition 1, right? The previous nums equals the current index nums, right? So I'm saying like the IDX minus 1 here and then IDX. And it's valid up to -2 points, meaning that this is a valid index up to this system here, right? So that means there's a valid partition up to this state, because you can find a valid partition here, and what comes right before it is also a valid partition. So that's condition 1. So if this is true, then it's a valid partition up to this index. So that's one such way that it can occur. Okay. Or, so that's one way it can occur. How else can it occur? It can occur if the previous 3 elements are equal. So if nums at idx minus 2 equals nums at idx minus 1, which equals nums at idx and v of idx minus 3. So that's basically saying if these 3 things are equivalent and this previous element of this partition is true. Right, so you found a new partition of size 3. That would mean the element that came right before it has to have a valid partition up to that point. Okay? So that's another way it could happen. And then we'll put the or here, just to be clear. And what's the last way that this valid partition could happen? If nums at idx minus 2 equals nums at idx minus 1 equals nums at idx, which is basically just saying, you know, if this was 3 plus 1, wait, no, yeah. So this was 3, and this element was 4, the minus 1 would be 3, right? And if this was 5, so minus 2. So this is basically saying that they all increment by 1, right? Because if this was 3, 4, 5, 4 minus 1, 3, 5 minus 2, 3. And again, it would mean that v idx minus 3 is a valid partition up to that point, right? So these are the 3 conditions captured. So we just need this v, we need to utilize this recurrence relationship in our system. So if we look at this example and we try to play this game just to show how this is supposed to work. All right, so we'll have this v value. Okay. So obviously, maybe what we should do is set the first value of the v value to true. And we'll use a t for true. And then we'll look at each value. So 4, 4, 4, 5, 6. So 4 is obviously not a valid partition because it's not the right length. 4, 4, well, 4, 4 is a valid partition, and what comes right before it is true. We'll do red for false and green for true. How about that? So that means that this is true. For this one, you could try the first condition and say, okay, this is true, but since this is false, that doesn't work. You could try the second condition and look at this, and since this is true, then this is a valid partition. You look at 5, you check these 2 first, doesn't meet condition 1, and these don't meet condition 2 or 3, right? So since that doesn't work, you know, it doesn't even meet the conditions, this is false. You could look at this now, since this is true, but 5 and 6 doesn't meet condition 1. It doesn't meet condition 2, but it does meet condition 3, and this is true. Therefore, this is true. And at the end, you just return that the last element in your system is -1. Right. So now you'll have true in your system. Okay. Now, I think so this has a runtime of O of n, where n is the length of the array, right? Because we just need to look at each element, and then for each element, we check 3 conditions. So it is constant, right? We kind of have to look. We have to look at a lot of stuff, but in terms of runtime complexity, this is constant, a constant operation, right? Because you just need to check some information to see if condition 1 is true, check some information to see if condition 2 is true, check some information to see if condition 3 is true. But besides that, you're not doing anything that scales with the input. So the runtime of this is nice, right? We have a time complexity of O of n. Now space in this orientation here would also be O of n, right? Because for each element, I save information if the partition up to that point is good. I'd say that I'm pretty sure that we can actually make this, we'll do it like this. We can make this O of 1, or we can make this constant if we don't save everything that we've done so far, right? Because at every point, like at this point here, you don't need, this information is no longer relevant, right? Because as long as we have information about up to here and here, right? Those are the only 2 points where we need to check if a partition is valid to continue our solution. So V doesn't need to have all the information in the array in terms of all the valid points where a partition could exist. It just needs to have the 2 most recent partitions, right? Or I guess you could say the 4 most recent partitions, right? You only need 4 total valid partition points in order to continue finding the solution as you traverse through the array. So we can cut the space-time complexity from O of n to just 4 elements, which is O of 1. Okay, so that's what we're gonna do. So let's go ahead and do that. Just trying to think about how we're gonna do this efficiently. So we'll have our valid array, which starts at 1, right? Because the first thing is true. Plus 0 times 3. Now the first thing that could be valid is at index 1 of our for index in range 1 to length of nums. So you check each one. How would we do this? So I'm trying to think about how I'm going to populate stuff. Let's just go ahead here and set v of 2. So let's manually do the first one, meaning since we're creating this v value, right? V is only going to be of size 4, and it's going to start out looking like this. So let's go ahead and just manually calculate this one, right? Because this will be true if they're equal and false if they're not automatically. And then we don't have to worry about like edge cases, because if we start looking at this index and there's 3 elements, like what are you going to compare to over here? So it's just easier for this problem if we just manually calculate this value and then use the loop for the remaining values. Okay. So v of 2 would equal, okay, what's the length of nums? Okay, it's at least 2, so we can always calculate this, it won't error. If nums of 0 equals nums of 1, okay. And then for the remaining indexes, everything's offset. Well, how are we gonna do this? Okay, so we have, sorry, I'm trying to think about, I know how to do this, it's just the cleanest way of doing this. Because I've already done something kind of dirty by manually calculating one thing, right? So, this can only be true. Well, condition 2 and 3 have to be true. So I'd calculate if this is true. And then I would, what? I would remove I'd calculate if this is true, find the value. Then I could pop the first element from it. Calculate if this is true, pop the first element. So I only really need 3 things in this array. Okay. Sorry, I'm just trying to think of, okay, so we depend what? So we have to check these 3 conditions. So at the end, you would pop the first value from V because you no longer need it, because every time you check an element, the first element in your size 4 array becomes irrelevant. So this could be size 2. So you only actually need 3 things in your array at any given time. So let's go ahead and check these 3 conditions now. So let's check this first condition. So if nums at index equals nums of idx minus 1 and v of negative 2. So what would that mean here? So these things are equal. Nums is this whole, no. Nums is this whole thing here. Negative 2 would be, so nums would be 3 elements when I'm checking this. So I would check the last 2, I'd check these 2, minus 1, minus 2. Because anytime I'm looking, I guess the idea, if I can make this just a little clearer. When I'm looking at this element, V will have this size. And it'll be true, false, true. So if I want to check if this is a valid partition, I need to then check if it's valid up to this point. So that'd be negative 1, negative 2. So if that's the case, then V append true. Else if nums of index equals nums of index minus 1, so now we can start at 2, equals nums of index minus 2 and V of minus 3, V append true again. Else if nums of index minus 2 equals nums of index minus 1 equals nums of index minus 2, right? So if this was 3, then this would be 4 minus 1 and 5 minus 2, 3. And V of negative 3. V append true again. Otherwise, we couldn't find a single condition that was met where the condition was met and we could validly partition the previous subarray. We append false. And at the end, every time we do an iteration, the oldest element becomes irrelevant, so we pop it. And then at the end, we just return a v of -1 is true. So if the last element can be partitioned. All right. So v of 2 let's just first do this. So let's print idx and let's print v to make sure that we're doing this right. So when we're looking at v of 2, oh, equals this, not equal. All right. Well, let's try that on for size. Okay, cool. So this is valid, right? So we have constant space, we have linear time. Now what I might feel inclined to do is make this a one-liner. I know. So we would make this a one-liner by saying if this condition is true, so there's 3 conditions. So this condition is true, if this condition is true, or if this condition is true. So if any of those conditions are true, and that means that we've captured all 3 conditions, we no longer need to do this pop thing. And look at that. Now, you can do it all in one line and you can be... So then you can make this even shorter. You can make this a 3-line solution because you can make it true plus false plus... And look at that. Just like that, you have a 3-line solution now just by making it really short. But I'm trying to make a habit of writing my short solutions after I write the more comprehensive solutions, right? Comprehensible, I guess. But yeah, so that's the idea. So someone might say, well, every time you do this loop, you have to shift all your elements down 1. So isn't that taking n time? No, it's taking 3 operations, right? And I could maybe make the array in reverse, and then you could easily pop the last element versus popping the first element. So, you know, this is making it slower, but it doesn't affect the worst case runtime, so I'm not gonna change it. Okay. So I hope this made a little bit of sense. I apologize if this is definitely one of my worst videos. You know, it's interesting when you make these Leetcode videos, just like when you do interviews, sometimes they're good, sometimes they're bad, sometimes you're better at explaining your ideas, sometimes you don't even have an idea, and that's why the beauty of the game is the luck of the draw. All right, peace out.